force on a current carrying conductors. Well, current carrying conductors are wires, right? For all intents and purposes, we will look at these as just moving charges. So we've seen what happens with individual charges, right? That was the last section. So here, there's just a couple things that I thought are worth reviewing. First is that current, right, which we usually represent with this I here. Current is just, right, the charges per unit time, right? It's coulombs per second, I think might be a standard unit. Now, usually we just use amperes for that. I didn't write that in here, but did I put the units? No. Okay, sorry. So 1 ampere just equals 1 coulomb per second. I know the textbook likes to put like these square brackets to let you know they're just talking about units here, not about actual amounts or whatever here. So that's the units for that. So we're saying basically you can think of it as like if each of these little charges here represented 1 coulomb, you'd have one of them, and you picked some point in space, right? When you're talking about current, and let's say I was like looking at some sort of, spot here, and I'm trying to say how many charges are moving past that position in space in 1 second, right? If it's 1 coulomb per second, that's what's going on there. Now, no, 1 ampere is a pretty good current. That would tickle if you were trying to touch something like that. More than enough, you wouldn't be able to let go either, which would really suck. Not to make this very morbid. For a wire with a length L, the speed of the charge, right? So remember, we just used the fact that V equals D over T. We know that. In this case, if you've got charges moving along a wire, the distance they're going to travel is L, and we're just going to leave it as T for the time that they take to go that distance. So now if we look at a wire, and remember, we just looked at what happened with individual charges. So we've got our wire here with multiple charges moving through it, and we've got some magnetic field. Oh, so this is represented, for a second there I thought this was weird. Now, I'm not drawing the magnetic field around the wire, okay? This is an existing magnetic field, and the current is going through the wire, right? So that's why all the magnetic field looks the same. So this represents a consistent or magnetic field that's coming out of the page, right? It's coming toward us. And we know the wire will produce its own magnetic field, right? Each moving charge will. And we're going to look at just how do those two work together to apply some sort of force to this. And so I already did the derivation over here. If we look at that, we can say the magnetic force on charges, this is the equation we sort of left off with in the last class, right? It's just QVB sine theta. We can replace V with L over T because that's the velocity that these charged particles would be moving with. And then we can just move that little T. You can see here we just move this little T over so it's associated with the Q instead of with the L. And that leaves us with Q over T. And we said Q over T was I. So basically we ended with the equation ILB sine theta. And we just have to remember this is for a current carrying wire. So if we have that information. Now, in this case, they're perpendicular, right? The charges are moving to the right. The magnetic field is coming out. So you could use the right-hand rule, and you can still just point your thumb in the direction the current is moving of your right hand. The magnetic field is coming out of the page. So I can't really lay my hand down flat. If I tried to draw my thumb here, it would go that way. But because the magnetic field is coming out, my hand sort of has to, the fingers of my right hand have to come out of the page, right? And that means that the force on this thing, on this wire, would be down. right? Just the same way I would do it if it was an individual charge. It's just lots of them. Okay, we'll look at an example. Ready for school or summer school to be over, a student puts up a flashing "School is out" sign 20 meters high to power the flashing neon lights. They run an extension cord up to the sign. The extension cord experiences a force of 8 times 10 to the negative 3 newtons. How much current is running through the extension cord? And as a note, Earth's magnetic field, which would be the magnetic field present here, is 5 times 10 to the negative 5 Tesla. Right, so it's not really high. It's good enough though, right? Like that's a okay magnetic field. It works. It certainly helps protect the planet from all those horrible charged particles the sun sends out this way. But it's not really strong. But by contrast, it's like I said, it's okay. Like a Tesla, a magnetic field of a Tesla is pretty good, right? Like you could really damage some electronics with a 1 Tesla magnetic field. So this isn't bad. But anyway, let's try to do the math here. Or let's take a look at this situation. So, and okay, I'll sort of suppose that here's the. It's hard to kind of draw this to say. Okay, here's the ground that we're on or whatever. I don't know if it needs to be curved or whatever, right? So we can imagine then that we've got our wire, our current carrying wire going up to the sign, right, where we've got our current. Our current's going this way. And if you can kind of imagine like Earth's magnetic field, if you draw it on the planet like this, right, it's usually kind of going. Let me get a different color for a second, right? It's usually kind of going this way, right? It's going like directly up or pointing directly north. So we've got a wire that's we can say is straight up and down, right? This is in the up direction. And so we'll basically just say, well, then just let north be into the page. Just for drawing purposes or to kind of see this. So that means our magnetic field would be, I don't know if I need to even draw that around. And we said this is and really here we just want to figure out the amount of force anyway. So we can say the magnetic force on this thing is just, we can use the equation ILB. And we'll just let sine theta be 1. And we're asked to find the current I. So we can put in the numbers. We know 20 meters. We know the force on this thing is 8 times 10 to the negative 3 here. So, or I suppose if I wanted to, just for simplicity, I could rearrange this, divide both sides by L and B. Sorry, that's a terrible L. You deserve better. Then I can put in the numbers just so it's only one step when I have to do that. The force was 8 times by 10 to the negative 3. The length was 20 meters. And the magnetic field is 5 times 10 to the negative 5. And that means the current in this thing is 8 amperes, which is a pretty good current. This must be a big, flashy neon sign. Oh, I didn't really, since I did the drawing again, you could use the right-hand rule here. You could say point your thumb in the direction of the current, right? So if you're using your right hand, you can say, okay, point my thumb up, and if I'm using my right hand, right, that's a weird hand, I know, but right, I have to lay my hand down flat on the page. So this would mean the force would actually be into the page. Oh, sorry. It would be to the right. Yeah, your fingers have to point in the direction of the magnetic field, if I'm not mistaken. So that means my thumb points up. My this would be kind of a side view of my hand, right? My fingers would be sort of pointing into the page, and so that means the force on this thing would actually be right. The force on this thing would be to the left or whatever. So it would be kind of neat. You'd see it essentially headed west. You'd see this wire sort of move a little bit to the west when you turned it on, or when which would be kind of interesting. And we figured out the current, so I guess that's it. Just because you're asking about the sine theta here too, because right, so anytime they're at, remember you want the component of the velocity or motion of the particle, right, that's perpendicular to the magnetic field. And so we're saying, look, this wire here is going straight up and down, right? And our magnetic field is 90 degrees to that. It's right into the page, right? Maybe it might be at a little bit of an angle depending exactly where on the earth it is or how the magnetic field is in that, but we'll just let it be 90 degrees, and sine of 90 is 1. So if you can make that assumption, like, just sort of go with it. But that's the reason there that I'm just letting that equal 1. If I would expect to, if there was some angle here, I'd be given that, or I could sort of figure it out.